how this can actually happen. So the selected subclasses here for lyases, we have dehydratase, and dehydratase is actually involved in the removal of the components of water to form a double bond. And for decarboxylase, it is involved in the removal of carbon dioxide from a substrate. Deaminase, it's involved in the removal of ammonia from a substrate. So as you can see in their names, the molecule that they are actually removing or forming as a byproduct are actually incorporated in their names. But if you have like hydratase, it actually means that there is an addition of a component, which is water, to a double bond. So here in our example, we have a substrate fumarate, and we have here our example fumarase. So most of these lyases, most of them are actually conjugated enzymes. So when I say conjugated enzymes, you might be wondering how do lyases actually catalyze these reactions? So most of them, as I have mentioned, are conjugated enzymes. So it actually means that there is a non-protein component that may be involved in this reaction, although it's not usually included in biochemical reactions. But when you look at their mechanism, there is actually a possible cofactor or coenzyme involved in the reaction to speed up the reaction or the biochemical process. And here we have fumarase enzyme. So the fumarase here, it actually we have the addition of water to a substrate. So from our fumarate substrate, we need to add our water in order to convert it to L-malate. So as you can see, the double bond here is removed. So wala na kayo double bond because we actually form a bond on this carbon. So it actually forms a bond with the hydroxyl group of water. And on this carbon, the hydrogen from water or the remaining hydrogen from water actually bond. So possibly there is a cofactor or coenzyme involved in the reactions of lyases. So the next one is we have the shapeshifter. So kani siya dali ra kayo siya ma-memorize because you have in its name the term isomer. So isomerase. We have isomerase is a Pacman mode, which is the shape shifter, wherein we rearrange dots into new patterns without adding or removing anything. So it doesn't actually change the atoms involved. So it actually just reorganizes it. So like rearranging a puzzle piece into a new shape. So for example, this actually happens in glycolysis, where glucose is rearranged into fructose. So we know that glucose and fructose are actually isomers. So those are the examples wherein isomerization reaction takes place. Okay, so let's take a look at the basic definition of an isomerase. Isomerase is an enzyme that catalyzes isomerization or basically rearrangement of atoms of a substrate into a reaction converting it into a molecule which is an isomer of that substrate. So we have here basically you convert A to B through isomerization reaction. Okay, so we have subclasses here for isomerases. You have racemases and mutases. So as you can see here, So it can be a racemerization reaction or a mutation. So in racemases, they actually convert D to L isomer or vice versa. And mutases, they actually transfer or there's involved a transfer of a functional group from one position to another in the same molecule. So as you can see here in our example, our substrate or reactant is 3-phosphoglycerate. So that means that our substrate, so here in the enzyme name, we have the name of the enzyme, which is phosphoglycerol, and then we just added a mutase. So what is the role of phosphoglycerol mutase in this reaction? It actually helps to transfer this phosphate group and rearranges the molecule, and we can now convert it into its isomeric form, which is 2-phosphoglycerate. So this is actually very important in metabolism because there are actually reactions or enzymes that they need a specific form of a substrate in order for the biochemical reaction to take place. Since we know that enzymes, they have a certain form, certain shape, so it's important to convert the substrate into the correct form or correct substrate. So in this case, from 3-phosphoglycerate, we converted it to 2-phosphoglycerate. Okay, so we're actually down to the last enzyme. So from ano na ba, naka-memorize na ba ito sa atong Pacman modes? Okay, so the next one is basically bond builder, or we will refer this to ligase. It actually connects two pieces together to make something bigger. So from earlier, we said na from a bigger molecule breaking down to smaller molecules. So now we are going to piece two molecules together to make something bigger. So let's say this Pacman mode rearranges these dots into new patterns without adding or removing anything. So it doesn't change what's there. It's just, I mean, it actually joins the two molecules. So it's like a molecular builder. It joins two molecules like gluing two puzzle pieces to make it a bigger in its shape. So let's take a look at its basic definition. So it basically means that putting those pieces together here, it actually, you need an input of your ATP. So you might be wondering how can this occur in biochemical reaction. So we need energy in order for this reaction to occur. So for example, when ATP is used, it breaks down to ADP and releasing enough power for the ligases to make a bond. So for example here, as you can see now, they only let's say substrate A and substrate B are joined together in order to form your product AB. So kana lang ang iyahang basic representation, and we're down to our last class wherein we have the EC6 class. Okay, so we have here our selected subclasses, wherein we have synthetase and carboxylases. For our synthetase, it actually helps in forming new bond between two substrate without participation of ATP. And your carboxylases, they form new bonds between substrate and carbon dioxide with participation of ATP. So let's see, for example, we have pyruvate carboxylase. So we have our substrate pyruvate. So we can also refer it. So we have pyruvate in the name of the enzyme. And here, since we have the participation of ATP, so we are including it to our reaction. So we have here ATP, and we need ATP in order for the reaction to occur or to convert pyruvate into oxaloacetate. So as you can see here, wala gipakita si what's this carbon dioxide, but it is actually a formation of a bond between pyruvate and we need carbon dioxide, which is probably a byproduct from the previous metabolic reaction. So let's zoom in a little bit. So as you can see here, so there are actually biochemical reactions, especially when it involves ligases, wherein from three carbon atoms, as you can see, it can form uh, a molecule with or a compound with four carbon atoms, wherein in this case oxaloacetate. So you can actually have a substrate plus carbon dioxide or any byproduct, or a substrate and or you can have two reactants in that case. So pwede siya reactant 1 plus reactant 2 can form your product, or you can use a byproduct with the help of ATP in order to form your product. And as you can see here, so you have your ADP since you already use ATP in this reaction. So there's actually the removal or your phosphate use. Since in pyruvate carboxylase, you cannot actually see it in this whole process because there is also a what's this, your cofactor involved in the reaction of pyruvate carboxylase. So that's why, as you can see here, we have ADP, phosphate, and your hydrogen over here. But when we go to metabolism, we can actually take a sneak peek in this reaction mechanism so that we will be able to understand further what is the role of these cofactors and coenzymes, especially in our key metabolic processes. So I think we are done for today. And for tomorrow, we will be discussing enzyme action and factors affecting activity, competitive, non-competitive inhibition, and the modes of substrate binding.